So we are going to make precise some connections between complex geometry and crypto systems. But before that, we saw today that Professor Dilip Patil explained basics through high school geometry via the linear equation, how it explains set of all points satisfying a certain linear equation and conic section, so on. So let's start from there. I invite the audience to my Algebraic Geometry 1, uh, which is also there in the same channel. Now, if even if we take non-algebraically closed fields like R, we see that R meaning real numbers, we see that equations or a set of equations can be solved for common solutions. So we saw in part 1 of my algebraic geometry series that an algebraic variety is defined as a set of zeros of a bunch of polynomial equations. So for elementary understanding, we saw that functions of the type fxy, which are polynomials in the polynomial ring rxy. Here I should mention that this R is the set of real numbers. So boldface R means real numbers here. So thus linear functions of the type ax plus by plus c form lines in R2. Similarly, degree 2 polynomials uh, were seen to generate nice geometric objects like the conic sections if uh, certain conditions are satisfied, that is if it does not lead to degeneracy. What Professor Patil explained, that they should be irreducible. If they factor out as linear polynomials, then they obviously give a pair of straight lines or parallel lines. That's what you saw in the lecture today. So the uh, second lecture today dealt with the manifold. So let us look at some of the connections. So we can look at algebraic variety starting from a real or complex manifolds. So we'll shortly see more precise definition of a manifold. Um, so the circle, which is a one-dimensional manifold, uh, is also the zero set of the polynomial equation fxy given by x square plus y square is equal to 1. It can be defined for any positive radius, but we will consider unit circle. So similarly, other conic sections are in fact real manifolds and simultaneously real algebraic varieties. So this class are called algebraic manifolds actually. But before that, let's just look into the topology or differential geometry setting of real manifolds. Let's see here. Um, so there is a very interesting, you know, caricature kind of a thing, but still it's a manifold. In this picture, we see that at every point on such a manifold, the neighborhood, just like what I say here, locally it looks like Rn. So here, since it's a surface, locally it should look like R2. So one can carve a neighborhood at point this neighborhood can be taken up as a disk, and that disk is homeomorphic to the disk in R2, right? So um, similarly, a disk-like neighborhood here, but that can be seen to be homeomorphic to R2. Similarly, I want to say what is not a manifold. See here, this hyperboloid kind of a thing at this center point, uh, uh, no neighborhood can be seen as homeomorphic to any neighborhood of Rn for any n. And therefore, this is not a manifold. If you just cut out uh, the cone without the vertex can be called as a manifold. But if you include the vertex, then that's a problem. That's a singular point actually. So essentially, uh, we should avoid such singularities for smooth manifolds. So that's the idea of manifolds. So so let me elaborate. Um, a manifold is something that locally looks like Rn for some n. For example, the circle looks like R. Again, I should make it boldface. Hence, it is a one-dimensional manifold in the language of differential geometry. We will make it mathematically precise. The phrase locally looks like, as I said earlier, the local neighborhood is is homeomorphic to a ball in Rn. Take the sphere, for example. Here we see that any point on the sphere is, it looks like a disk in the sense up to homeomorphism. So we can we can make a homeomorphic map of that neighborhood to a disk, and therefore it's an open ball in R2, and therefore it's a two-dimensional manifold. So this arrangement of um, making the whole manifold look like Rn means that you have a union of local neighborhoods which are charts, and each chart has a corresponding homeomorphism to some disk in Rn, and need not be disk also, but we are trying to make this picture clear for a beginner. So that chart description gives rise to what is called as a differentiable atlas, a differentiable structure through atlas. Okay, so this is a sphere in the language of geometry is a two-dimensional manifold. So let me give more examples. Loci of polynomial equations like ax squared plus bx plus c is equal to 0 give rise to manifolds, provided the equations are chosen appropriately. The torus S1 cross S1 is a two-dimensional manifold. This is what maybe in this picture, we just look at this part. This part is like a torus. So also we can look at higher dimensional uh, examples. Like for example, S2 cross S2 is a four manifold. There are a variety of examples of manifolds, and we are not exhaustive enough. I'm just giving you this product like space, just to give to support our intuitive sense, but you can give your own examples. So interestingly, all my examples can be obtained by considering algebraic variety structure using appropriate polynomial systems. For example, we have a theorem that if X is an algebraic variety and Y is an algebraic variety, X cross Y can also be given the structure of an algebraic variety. So S2 cross S2 or S1 cross S2, S1 are algebraic varieties in by appropriate polynomial systems. So now an interesting class of manifolds which have simultaneously an algebraic variety structure are complex submanifolds in PNC. This came up in today's lecture. This is due to Chow's theorem, which says that complex submanifolds of a projective space over C is actually an algebraic variety. The compact Riemann surfaces fall under this class. All compact Riemann surfaces can be seen to have an embedding in an appropriate projective space. In fact, there are neater examples. What is the lowest dimension in which we can embed compact Riemann surfaces? These theorems are available, and one can look into the literature. So I'm coming to the end of this snippets, just to support this FDP that is going on. I wanted to make this quick lecture. So we comment on the connection that we saw between complex manifolds and cryptosystems. The elliptic curves, which are made famous due to the ECDLP algorithms, are actually manifolds with a group structure on them. That means they are abelian varieties. So more deeper aspects are used to make effective algorithms. For instance, the Picard group of devices on an elliptic curve, and also higher dimensional abelian varieties. Then Jacobians of an elliptic curve. They are considered to give effective encryption, which are supposedly very effective in the sense that complexity of making uh, trapdoor functions is easier, whereas the script analysis on them will be difficult. That's what maybe from tomorrow onwards, people who speak on crypto systems will focus on. So thank you for watching this video. I just wanted to make this video to help people to set the context in which we have devised this 5 days program on complex manifold and crypto systems, because um, parallelly we can look at this pure mathematical theory of complex manifolds and also crypto systems, and at the end we can sort of give connections, and it's kind of nice to see that there are applications in modern cryptology. So thank you.